All right. So we have these two vectors, u and v, and we had to sketch a vector that represents u plus v, and then a second vector that represents u minus v. And it looks like every single group got the u plus v without too much trouble. Yeah, good. Okay, so when you're adding two vectors together geometrically, I was learned, oh my goodness, and that's recorded too, that's great. I was taught that when you say it, you say tip to tail. So that's where my brain has always gone. There are some teachers who don't teach tip to tail. They teach what's called the parallelogram method of adding vectors. Either one's fine, Dorsa, you did the parallelogram. It was a team effort. It looks fantastic. Yes, that is a beautiful parallelogram, back corner group. All right. So tip to tail really just means, like, if you think of the front of the arrow as the tip and the back of the arrow as the tail, you take either one of the vectors. I'm going to take v, and I'm going to move it over to the end of u so that, I mean, it doesn't have to be perfect, but roughly so it looks about the same. And then, so that's my new v. And then once they're lined up, so tip to tail, the tip of this vector is touching the tail of this vector, then you go from the beginning to the end, pretend that that's straight, and then that would be u plus v. Now, what the back corner group did was they did the same thing. They put v tip to tail, but they also kind of redrew u. So you kind of make a parallelogram out of it, and then the diagonal of the parallelogram is the sum of the two vectors, right? So that's what some people call the parallelogram method. Really doesn't matter. So I just do tip to tip, but whatever floats your boat is fine. So to do u minus v, I'm going to just erase this. Yeah, do I want to try and copy? Maybe I can try to copy. Copy. Otherwise, I'll just draw. Paste. Oh, hey, it worked. Look at that. Okay. All right. So to do u minus v is really the same as u plus negative v, right? Well, what is negative v? Negative v is just v pointing in the opposite direction. So negative v, if this is v, then negative v looks like that. So now you do u plus negative v, and you do them tip to tail. I'm going to move this up here. And you know what? I can take this, since I already drew it, and put it right here. And then my u plus negative v, there's my u minus v vector, which I think most of you got that one too. So yeah, beautiful. Look at that. You even labeled the negative v. Wow. All right. Good. Okay. This one had a little bit of an issue, but that's okay. So now do we know? Yeah, see, that's the whole point, is just to learn, right? Good. So that's what we're doing today. Today we have a huge lesson with a lot. 12-2A, vectors in space. Today we are going to learn every possible nut and bolt about vectors there is to know. And then, I mean, it's a huge lesson today with a lot of notes. So I apologize that there's 10 million notes today. But once we get past it, tomorrow is all applications. So tomorrow is where we're going to use all those resultant forces to solve problems with, like, airplanes. You know, an airplane's flying at 10 degrees southwest with a headwind coming from this way, right? That kind of stuff. Yeah, it'll be so much fun. Or the fun ones, like you have a picture hanging on a wall and you have different tensions on the cables, right? We'll be doing those kinds of things tomorrow. It'll be great. All right. But today is just to learn as much as we possibly can about vectors to get you ready for tomorrow. So, what is a vector? So many quantities in geometry and physics, such as area, time, and temperature, can be represented by a single real number called a scalar. Yes, Jack?
we ever going to have Mr. Moss in here as a guest professor?
Guest professor. All right. Other quantities like force and velocity involve both magnitude and direction and cannot be completely characterized by a single real number. To represent such quantity, you can use a vector. Vectors have magnitude and direction, right? Okay. So the directed line segment, and that's what this thing is, directed line segment has initial point P, terminal point Q. I'm not going to test you on vocabulary, but I'm going to use it a lot. So just so you know, like if I say, hey, where's the initial point? That's like the starting point, right? And then terminal point is the ending point of the vector. It's what it's pointing to, right? So initial point, terminal point. The magnitude, which is magnitude of a vector, can represent a lot of different things. Technically, literally, just numerically, it's the length of the vector. But in context, the magnitude can represent all kinds of things, right? So tomorrow we're going to be using magnitude to represent velocity and force and weight and all these different things. But as far as mathematically, it's just literally the length of the vector, right? And so we denote magnitude by putting the vector, sometimes you'll see it in single lines and sometimes you'll see it in double lines. I will almost always write it in single lines just because that's the easiest way to type it on your keyboard. And I think your book also just uses single lines. But once in a while, you'll see some other resource that does double lines. It's the same thing. It just means magnitude. All right. Vectors are normally denoted by lowercase boldface letters such as U, V, and W. So you see vectors listed in a couple different ways. So one real common way is if you label the beginning and end points with capital letters like PQ, you write PQ with this arrow over the top, that's vector PQ. Or if you don't want, like, this is for typing. Honestly, most of these notations are from old time when people didn't have access to fancy keyboards and all kinds of symbolic notation. They had to type what they could on their typewriter. So we gave vectors single letter, bold letter names like U. So anyway, so this is, you'll see this a lot. Just a single lowercase letter that's in bold means it's a vector. All right. Equivalent vectors have the same magnitude and direction. So if we put the same displacement, you don't use the word displacement very much though. Really, same magnitude, same direction means the two vectors are equivalent. And then a vector with no displacement is called a zero vector, denoted by 0, right? If the vector has no length, if it's just a point, then it's called a zero vector. Okay. Does anyone need more time on this screen before I move on? Okay. Okay. All right, addition of vectors. I'm not going to go deep into this. We already did this with the warm-up. If you need to add geometrically, you line them up tip to tail and then connect the initial point of one vector to the terminal point of the second vector, and that is what's called the resultant. We'll get into that tomorrow. But when you add two vectors together, that sum, which is called the resultant vector, it's just when you line them up tip to tail, you add them. Subtracting vectors is just the same as adding vectors, except you make one of the vectors negative and line them up tip to tail. And to make it negative, you're just reversing the direction. When we multiply vectors by a scalar, so multiplying by a scalar changes the magnitude. The only way it changes the direction is if it reverses it, but it will never like rotate it or anything. Right? So when you multiply by a scalar, so like here we've got vector v. So if I take vector v and multiply it by a half, it just makes it half as long, right? You're taking the whole vector, just half of it, right? Or double it, -1 times it, so that reverses the direction, and then -3/2 reverses the direction and makes it 1.5 times as big. So multiplying a vector by a scalar changes the magnitude, and the only way it will change the direction is if you multiply by a negative, it'll change it to the opposite, but it's never going to like rotate it 10 degrees by multiplying by a scalar. You have to do a different thing to rotate. Okay. Any questions so far? I'm kind of chugging through. It's pretty cool stuff. All right. And remember, all these smart boards are online. All right. On the coordinate plane, we represent a vector as an ordered pair in these like corner brackets, right? So when you write a vector, you write them in these little corner brackets, A, comma, B. So A is the horizontal component, B is the vertical component. So when we write a vector in what's called component form, it means we're writing it with those little corner brackets with an X or a horizontal component and a vertical component. That's called component form. Vectors don't, well, I'm going to show you this in just a second. Equal vectors, vectors with the exact same horizontal and vertical components, right? So they're equal. They're the same vector. All right. So how do we get component form? How do we find out those two numbers? Well, if you're given the initial and the terminal points, you just subtract them, and that gives you your vector. So we're going to practice this a little bit. I hope I have the answer here. Don't look. Okay. All right. So when you have the initial, if we have an initial point 4, -7, and a terminal point -1, 5, and the order makes a difference now. It's not like you can go in either direction. You have to do terminal minus initial. You have to do ending minus starting. Otherwise, you're going to reverse the direction of your vector. So when we do our ending minus our starting, so our vector V, so it's just basically x minus x, y minus y. So you do your x minus x, -1 minus 4, and your y minus y, 5 minus -7. So this vector would actually have component form of -5, 12. Now here's the thing while you're writing. This is the thing that freaked me out when I was first learning vectors, and then later on when I was older and I had to kind of relearn vectors, I got very confused, especially when I got into applications, because when I see the vector -5, 12, my brain thinks, well, let's see, what does that mean? Like -5, 12, because that looks like an ordered pair, right? So, but I need, like, where is it located, right? Vectors have no location. A vector, all it has is magnitude and direction. That's it. You can take a vector and move it anywhere you want. It makes no difference because it doesn't have a location. It just has magnitude and direction. Now, if you want to know something about this vector, technically, to find the magnitude and direction, the way you could sketch it is to go to the point -5, 12. Okay, that's 12. So if we sketch the point -5, 12, well, this vector then, if we drew a vector from the origin to that point, that would be a vector that has that magnitude and that direction, right? So, but really, this vector isn't that one because this vector, it says that it had an initial point of 4, -7, 4, -7, and a terminal point of -1, 5. So this vector actually was sitting here when we created it. So the resultant vector doesn't tell you anything about where it actually is, but that's okay because vectors have no location. They just don't. They're like mysteries floating around in the air. But if you want to see like their actual length, like what they look like, what direction they're in, and how long they are, you can, all you have is the vector, you can sketch that point like an ordered pair, connect from the origin, and that'll give you the length and the direction, right? You'll get a visual. But just know that's not necessarily the location of the vector that was being described. Like this one actually started down here. Okay. All right. Okay, here's where we get into the nitty-gritty. How do we find the magnitude? Magnitude of a vector? Well, if I drew this guy right here, right, and this is the point, -5, 12, and I said, hey, what's the length of this vector? What could you use? Distance formula? Yeah, just Pythagorean theorem, right? Your x is 5, your y is 12, right? 5 squared plus 12 squared equals length squared, right? It's just Pythagorean theorem. So the same thing for vectors. When you're finding the length of a vector, it's just the Pythagorean theorem. It's just the square root of a squared plus b squared if your vector is AB. All right, so just for the heck of it, everyone take a minute and find the length of the magnitude of that vector. I'm curious if you can do it with no. Zach. It is 1. Very good. All right, did you know it was 1 without having to do all the math? Yes. Did you guys hear that? Zach recognized it was a 5, 12, 13 triple, right? Yeah, isn't that great? I know. See, those Pythagorean triples, they come in handy, right? So anyway, if you didn't know that, it's not like it's the end of the world. So the magnitude of W is the square root of 5/13 squared plus -12/13 squared. So doing all the math, you get 25 1/69 plus 144 1/69, which is 169 1/69 or 1. So you can do it the long way, right? Always works. Nothing wrong with it. But recognizing the triple is nice. All right. Any questions about how to find magnitude? You're going to be doing that tonight in your homework. All right. Algebraic operations on vectors. You do not have to write all this down. I promise you, as soon as we do a couple, you're going to be like, this is like so easy. I wish I was doing this all the time. So let's just, oh, I thought I got all my answers erased, but I didn't like scroll down enough. Okay. All right, I have 3 problems. So if V is the vector -4, 1, and W is the vector 2, 3, I want you to find what you think is 2V, W minus V, and 2W plus V. And I'll give you a hint. These are really easy. So take a minute and see if you can figure these out on your own. 1 minute of silence first, then 30 seconds of checking with your neighbors. All right, 2V. How do you find 2V? Vikram, how do you find 2V?
Just multiply the 2 times.
There you go. Here's double V. Y'all get -8 too? Good. W minus V. So W, so X minus X, Y minus Y. So, or horizontal minus horizontal, vertical minus vertical. So you get 6, 2. All right, and then 2W plus V. So you're going to double W and then add V. So you get 4 minus 4, which is 0, and 6 minus 1, which, 6 plus 1, which is 7. Adding. All right, good. Any questions on algebraic operations with vectors? Piece of cake, right? All right, we're getting there. Now we're going to start getting into a little bit more stuff. So a little bit heavier stuff. Unit vectors. A unit vector is a vector with a length of 1. That's why it's called a unit vector. Now, the two primary unit vectors when we're in 2 dimensions, and don't worry if you're thinking, when are we going to get out of 2 dimensions? Didn't you say in space? That's in about 10 minutes we'll get out of 2 dimensions and go to 3. But right now in 2 dimensions, we have the vector called I, which is the unit vector in the positive x direction, and it's vector 1, 0. J is the name of the unit vector in the positive y direction, and it's vector 0, 1. Any vector can be expressed as multiples of i's and j's. So if I have vector AB, so here, I'll just talk in terms of this guy. If I have vector -2, -5, well, let's just think about this. This would be -2i minus 5j. Why? Well, because -2i, that would be so -2 times 1, 0 minus 5 times 0, 1, right? I is the vector 1, 0. So you're taking your horizontal component times 1, and then your vertical component, and your vertical component over here times 0, right? And here, your horizontal component times 0, your vertical component times 1, and you end up, so -2 times 1, 0, minus 5 times 0, 1 gives you the vector -2, -5. So you can write this vector as -2i minus 5j. Now, why would you want to? This notation actually comes in really handy when we have to do heavier operations with vectors. So once we get into things like cross products and then we start having to do all this other stuff with vectors, it makes it easier. It also, just, in days old, helped people, again, use typewriters with vectors. A lot of notation I found with vectors, the explanation was because it was easier for people with typewriters. So anyway, but it really does help you, especially when we get to cross products. So we will use this kind of interchangeably from time to time. Our old book, I don't know what the new book does, but I know the old book used the IJ notation almost exclusively. And I think it was just because it's easier to type. So anyway, I like to go back and forth. It's really no much harder to put a corner bracket than the letter I. So anyway, but those are called your unit vectors, the I and the J, your unit vectors, one in your horizontal unit vector, your vertical unit vector, I and J. 1, 0, 0, 1. Oh, I missed this guy. All right, let's try, let you guys find this. So suppose vector U is -2i plus 9j, and vector V is 3i minus j. Find 2u minus 3v in terms of I and j. Again, this is nothing more than combining like terms. It works just the same as traditional algebra. if we do just the i's first, so 2u, if we're just doing the i's, would be negative 4i. So we're going to do minus 3 times v, so negative 4i minus 9i. So we end up with negative 13i. So you guys got? Okay. Negative 13i. And then same thing with the j's. So we get 18j plus 3j, so plus 21j. Did you all get plus 21? So plus 21j. And that's your answer, and then you're done. Tejas, you have a question?
No, I just did something else rather than doing what I was supposed to be doing.
Oh, okay. Do you understand it okay?
Yeah, I just converted it back. I converted it back into like the original vectors, and then I was adding all of that, and then converting it back. It was not.
That's okay.
Not ideal.
I didn't tell you what to do, and there's nothing wrong with what you did, right?
I just realized this is much easier.
It is a little easier. Yeah, but that's okay, right? That's how we learn. All right. Good. Unit vector in the direction of v. This we're going to be using a lot, way more than I ever thought we would the first time I learned this. So, if v is a non-zero vector in the plane, then the vector u, which is v over the magnitude of v, has a length of 1 and is in the same direction as v. So what you're doing is you're taking your vector v, whatever it is, and you're dividing it by a scalar, which is really the same as multiplying by 1 over a scalar, right? So if your vector, say your vector has a length of 5, and you multiply the vector by 1/5, you're then changing the length down to 1. So what ends up happening is you get a vector that's got the same direction still, because the proportions between horizontal and vertical are still the same, because they've just been adjusted by a scaling factor, and that scale factor is just taking them down to a length of 1. So any vector divided by its magnitude has a length of 1. It's called it's a unit vector, but it's in the direction now of this original vector v. So take a vector, divide it by its magnitude, you get a unit vector in the same direction. All right, so if we want to find a unit vector in the direction of this one, negative 2, 5, and then verify that it has a length of 1. So I want you to take a minute, find a unit vector, let's call it u. I want you to find a unit vector for v, and then I want you to just verify that the magnitude is 1. That's really just doing a quick Pythagoras on what you already had done. What you need to do is find the magnitude of v. So that's just the square root of 4 plus 25, or root 29. So your unit vector in the direction of v is just your original vector divided by its magnitude. That's all it is. So you just take the vector, divide it by its magnitude. If you want to write it like this, that's fine. If you want to write it like this, that's fine. It gets a little cumbersome though. Like I usually just go like this. So, but they're all correct, right? And all of those three are equivalent vectors. So they're all fine. Now to verify that this vector really is a unit vector, what are you doing? You're just doing, like if you do it like this, you're doing Pythagoras on this. Well, really, when you're finding, if you find the length of this guy, well, we know the magnitude of this guy is root 29. So the magnitude of this would be root 29 over root 29, which is 1. Here, let me say that better. So the magnitude of u would be the magnitude of this guy divided by that scalar, which is 1.
So the unit vector is represented by the letter u, right?
No, u is for any vector. We're just calling it u because v was being used. We could have called it q. The only unit vectors that have real names are I, J, and K. Oh, you haven't done K, but I and J for you. In 5 minutes, we'll introduce K. Okay. All right. Now, we're going to take this up a notch. This one, I could teach you how to do it, but I'm not going to. I want you guys to see if you can figure it out in your groups. Find a vector V with a magnitude of 8 that's in the direction of U, -3, 3. There's a reason I'm asking you to figure this out on the same screen when I taught you how to find a unit vector. So I'm going to have you guys, all right, I haven't sat down with all of you, but I've sat down with many of you, and it looks like quite a few of you figured out what to do. Or at least we're in a group where somebody figured it out, so that's wonderful. So here's the thing. We want a vector that has a length of 8 in the direction of -3, 3. Now, is -3, 3 a unit vector? No. What is the magnitude of -3, 3? Well, it's the square root of 9 plus 9, which is root 18. So the length right now of vector U is root 18. That's okay. So what do we need to do to get a vector that is a unit vector in the direction of U is take U and divide it by its magnitude. This is a unit vector in the direction of -3, 3. All right, so now we've got a unit. What's the length of a unit vector? 1. That's why it's called a unit vector. So now we have a vector of length 1 in the direction of -3, 3. We want a vector of length 8. So what do we need to do with this? Multiply it by 8. So now if we do 8 over root 18 times -3, 3, this would be a vector of length 8 in the direction of the original vector. So I'm going to draw a picture real quick. All right, so if you take a vector, so we have -3, 3, right? So we got a vector going out that way. So then you divide the vector by its magnitude. When you divide a vector by its magnitude, all it does is takes the same direction, but now it makes it with a length of 1, right? So you've taken this vector with a length of root 18, and you've taken it down to a length of 1, and then you can make it any length you want. Once you turn it into a unit vector, now you can expand it and multiply by anything, and you've created a vector of length whatever in the same direction. So for us, when you multiply by 8, now you get this nice vector, same direction of length 8. Does that make sense? Okay, so take the vector, divide by its magnitude to turn it into a unit vector, multiply it by 8, and then you've got a vector of length 8. Now here's the beauty of this. This is what, the first time I was trying to make notes the summer before last, so the summer of 2018, this didn't hit me until I was in class, was if I have a unit vector, so if I know that this right here, if I know that this is a unit vector, then any number that's in front has to be the magnitude of that vector, which is going to come in really handy because any vector written in trig form is going to be a unit vector. So when we write vectors in our trig form, they're going to end up being unit vectors, and then whatever the coefficient is ends up being the magnitude of the vector. It's really nice. So anyway, all right. I think this is the last slide, before we get into 3 dimensions. Okay, So let V be a vector in a plane with an initial point at the origin. The direction of V is the smallest possible angle in standard position formed by the positive x-axis and V. So in other words, guys, your direction of your vector, just for now, it's the same as like how we measure angles in regular trig. So it's always from positive x-axis and it's always going counterclockwise. You can, again, have a negative direction if you go clockwise and a positive direction if you go counterclockwise. So this angle right here, that's considered the direction of the vector. So if the angle is 35 degrees, then the vector has a direction of 35 degrees. So it's whatever this angle is. You know what's crazy is we kind of make a switch now from radians to degrees. Most of the problems we will do in this class will be in degrees. So just get used to it because we're kind of, I don't know, it is how it is. So you'll be using a lot more degrees because we do a lot more applications and most applications are done in degrees. So anyway, we're going to do a lot of degrees in this class. Now, this should be a review. We talked about this last year when we did parametric and polar. The horizontal component, if you think of this, do you guys remember with polar, we called this R? And this was r cosine theta and r sine theta, right? It's the exact same thing, except instead of calling it r, we're calling it the length or magnitude of v. So your horizontal component of your vector is magnitude times cosine theta, and your vertical component is magnitude times sine theta. So when we write in trig component form, which I don't know how far down I go to get there. Anyway, so if our vector, whatever our vector is, so ai plus bj, so whatever the magnitude of that vector is, if you do magnitude times cosine theta, that'll give you your x value, your horizontal component. Magnitude times sine theta, that'll give you your y value, your y component. Now, how do we, did I put on here where I calculate? The direction. Oh, I haven't. No, that's right. I don't teach it to you. I make you figure it out. Okay. All right. Does everyone have the whole, like, this and this written down? Okay. All right. Blah, blah, blah. Okay, so when we write, I didn't write it anywhere, but this is normally called, or this is the same thing as the cosine theta, the sine theta. This is often called trig component form. So you're writing the same vector, but instead you're writing it in terms of the trig components, the horizontal component and the vertical component, which are written in terms of the angle, the direction of the vector. So trig component form. All right, so a vector v has a length 4 and a direction, oh, we're back in radians, of pi 6. Find its horizontal and vertical components. I give you 30 seconds. Go, 29, 28.
We're still writing down.
Wait, you want like a number, or can we give it to you in trig form?
Oh, can you write it in trig form?
Yeah.
You can do the cosine and sine of pi 6.
I don't remember. I forget you did circle every year. I have to remember. I forget you sign.
Pi over 6 is that one.
The first one.
It's root 3 over 2.
Yeah, it's root 3 over 1/2. Okay. Oh, and then it's 2 root 3 I plus 2. Yeah, in terms of I, just get rid of the bracket.
Yeah.
I get one to do it. For now.
All right, the horizontal component. So the magnitude is 4. It'd be 4 cosine pi 6. What's the cosine of pi 6? 3/2. See, you're trying. 3/3. So the vertical component is 4 sine pi 6. What's the sine of pi 6? 1/2. So the vertical component is 2. So if we wrote vector v in terms of I and j, we could say v equals 2√3i plus 2j. Since both the horizontal and the vertical components are positive, does that make sense with an angle of pi 6?
Mhm.
Yes, first quadrant, pi 6, positive, positive, positive x, positive y. All right, last two-dimensional stuff, and then we go into 3 dimensions. So first, you're going to find the magnitude and direction of vector u. I haven't taught you how to find direction. I think you might be able to figure it out. If you're really stuck, consider drawing yourself a little triangle. So like -3√2/2. So we're like here, right? Think of it like this. Like -3.
Yeah.
Remember you're finding. So let's talk like there are easier ways to do this, but and one of the things to, if you really want to make your life a little bit easier when you're doing magnitude, you can pull out common factors. So like if you want the magnitude, you can pull that 3/2 out and then do times the magnitude of the rest of the vector, the √2 thing, right? And just do it that way. Anyway. So, but if we do it the long way, so we have square, so we get the square root of 9 times 2/4, so 9/2 plus 9/2. So we get the square root of 18/2, which is the square root of 9, which is 3. Okay. Did everyone get 3 for their magnitude? All right, angle. There's a lot of ways to do the angle. What I was trying to get you to see, and for this one, it's like a freebie. You could have guessed the angle if you think about it, right? Because we're going out and up the same distance, which means this is really just like a pi-4 angle, but we're in the second quadrant, so it's just 3 pi-4, right? However, what if it wasn't? What if it was like, 124.783. How are you going to know, right? What do you do when you need to find an angle? So if you know the x and the y and you want an angle, what function do you use? Use tangent, right? So your theta is just the it's the arctan of your y over your x. I'm going to write it as like a kind of like a formula. So it's the arctan of y over x, which is actually the same as it was when we did it with polar last year. So your theta would be the angle whose tangent.
You have like all 3 sides.
3√2/2 over
You can also just do
-2/2.
like.
So it's really the arctan of -1. The arctan of -1 technically is negative pi-4 because we've talked about primary angles, except we have to be in the second quadrant because of where this guy is pointing. So because of that, we can't say negative pi-4, so we got to say 3 pi-4, or it's got to be an angle that's in the second quadrant. Okay, so for that last one, you do the same thing. First of all, the magnitude, without doing any math, what's the magnitude?
3. Oh, last one.
It's 5. It's a 3, 4, 5, right? Okay, magnitude is 5, and then your direction would be the arctan of -4/3, right? Whatever that is. All right. Okay, don't write this down. All right, 3-dimensional vectors. Everything is exactly the same as two-dimensional vectors. The only difference is that now there's like a third number. So when you're doing a length, instead of a squared plus b squared, it's a squared plus b squared plus c squared, just like what we talked about yesterday. Instead of just I and j, you now have I, j, and k. Unit vector in the x direction, unit vector in the y direction, unit vector in the z direction. Everything, all the operations are exactly the same. The only difference is that instead of 2 numbers now in your vectors, you're going to have 3 numbers in your vectors. Just so you know, this lesson used to be done over 2 days last year, but the new book is set up so different that I'm squishing. I had to condense this into one because I wanted a whole day for applications. So tomorrow is going to not feel so squishy. All right. Okay, so if we needed to find the component form and magnitude of V having an initial point of -231 and a terminal point of 0, -44, so tell me first, all right, out loud, this is the beginning, this is the end, tell me vector V. What's the first component? 2. How do you find a vector? You subtract end minus beginning. End minus beginning. So 2, what's the next one? -7, 3, right? So there's your vector. If you wanted to find the magnitude of this vector, you would, so the magnitude of V, this is how, I had this already, but I'm just going to write it out. So it's the square root of 4 plus 49 plus 9, which is the square root of, what is that, 62? Okay, 162. So then a unit vector in the direction of V, so unit vector in the direction of V would be 2, -7, 3 over root 62. It's exactly the same as 2 dimensions, it's just that now there's 3 numbers instead of 2. Everything that you do that's in 3 will be exactly the same. All of this kind of stuff, the negative and the positives, that's all just exactly the same. You won't be asked to sketch a graph, although I think in your homework tonight they might ask you to do matching on graphs. And that's it. So I want to talk for 25 seconds